Hello everyone. In the previous video, we discussed about Altex's EEPROM peripheral. In today's video demonstration, we're going to take you through how to configure analog to digital converter in Altec HT66F3195 microcontroller, which comes in 28 SSOP package. The Altec microcontroller features a multi-channel ADC that directly converts external analog signals like those from sensors and internal signals such as reference voltages into a 12-bit digital value. The specific signal to be converted is selected using the SAINS and SACS bit fields. External channels are automatically disabled when internal signals are chosen. The device supports input channels like AN0 to AN11 along with various internal voltage options such as AVDD, VVR and their scaled values. This flexibility allows seamless integration of both external analog signals into digital systems. Explanation of the code. This code demonstrates how to use analog to digital converter on the HT66F3195 microcontroller to read an analog signal from AN8 channel and store the result in a variable called ADC value. Key sections of the code. Watchdog timer configuration. The watchdog timer is enabled to ensure that if the microcontroller gets stuck, it will reset automatically to avoid locking up. Setting analog input pins PBS 11 and PBS 10 bit to configure AN8 as input channel. Configuring ADC. The SADC0 selects AN8 as input channel for the ADC conversion. The value 0x00001000 refers to the section of AN8 in the register. The SADC1 register sets up the ADC clock and reference voltage. You should refer to the datasheet for exact configuration option based on your system requirement. Coming to ADC2 register, this configures the ADC with the default settings, which is typically sufficient for general use. The ADCEN bit enables the analog to digital converter, allowing it to start converting analog signals to digital values. We are adding a GCC delay. A small delay is added to allow the ADC time to stabilize before initializing the conversion process. In the while loop, we are clearing the watchdog timer. The infinite loop keeps the program running continuously. The ADC conversion is started by toggling the start bits from 0 to 1 and again back to 0. Program waits till the ADC conversion is finished, indicated by the ADBZ flag becoming 0. Combining ADC results. After conversion is complete, the result is split into two parts, the high byte SADOH and the low byte SADOL. These results are combined to form a 12-bit result and stored in the ADC value variable. Conclusion. This code continuously reads an analog input from AN8 on HT66F3195 microcontroller, converts it into 12-bit digital value using a built-in ADC and stores the result in ADC value variable. The ADC conversion process is controlled in a loop, making it easy to implement real-time analog to digital conversion in embedded applications. For practical demo, we'll be using HT66F3195 development board and our new programmer called E-Link Pro 2. We'll connect the external 5V power supply to AN 8-pin analog input pin. Ensure the Vref reference voltage is also 5V to match the input voltage. This is typically for many microcontrollers. So now let us connect the programmer to the microcontroller via our PC. As you can see, our new programmer E-Link Pro 2 has been connected to the microcontroller. Now let us click on OK. Add a breakpoint near no operation and run the code. We'll apply a breakpoint near ADC value to read the digital values in the watch window. Now let us build the code. Once the build is successful, we'll run the code. As you can see, we are getting a ADC value of 80, 16, which means the external power to the analog pin is 0. Now we'll switch on the power supply to provide 5V externally to the analog pin. And again run the code. As you can see, we are getting a ADC value of 4080, which is near to the maximum ADC value of this microcontroller, which is 4096 because of 12-bit A2D resolution. To calculate the digital value back to the whole analog value, we use a formula ADC input voltage equal to V reference multiplied by ADC digital value divided by ADC resolution. The V reference is 5V and the A2D digital value we are getting is 4080, which will be divided by the resolution, that is 4096, which roughly gives you a voltage of 4.98. Thank you for watching this video. For more such informative videos on how to use Haltech microcontrollers for embedded system development, stay tuned to our channel.